Hello, my name is Teja Riccardi, and the title of my senior project is Multi-Criteria Flowshop Scheduling Optimization. Here is a quick agenda of my presentation. First, I will be giving a quick introduction. Following this, I will be quickly going over my problem statement. After this, I will be giving a quick demonstration of a flowshop visualization. After I'm done with this visualization, I will be presenting my objectives and deliverables. And then I will be displaying my design and code of my implementation. Finally, I will go over the results and the conclusion of my project. So what is a flowshop? A flowshop is a manufacturing environment where different products follow similar processing steps. Take, for example, car manufacturing. Every car model has the same sequence of processing steps, but each model takes different times at each assembly station. For example, imagine you have a mid-sized sedan and a minivan. Both of these vehicles go through the similar steps, but they both take different amounts of times at each of the assembly stations. And so right here is the problem statement of flowshops. Flowshops receive a diverse list of orders every day. It is a common manufacturing challenge for flowshops to complete these orders on time while maximizing throughput. I would like to define two terms. And these two terms are throughput and total tardiness. Throughput is defined as the number of products that are manufactured in a set period of time. For example, a throughput of a flowshop could be 400 parts per hour. Total tardiness is defined as the total tardiness of all the jobs in the flowshop. For example, if you have 10 parts and each part is late by 10 hours, the total tardiness would be 100 hours. I'm going to give a quick illustration of a flowshop. Let's remember that in a flowshop, each part follows the same processing steps at the same machines. And so in this flowshop, let us imagine that we have two machines, each labeled 1 and 2. And that for each part, they first start off at raw materials and then flow into machine 1, then get processed at machine 1, and then afterwards flow into machine 2, they get processed at machine 2, and then finally end up in inventory. And in this scenario, let us say that we have three parts labeled Part A, Part B, and Part C. And then for Part A, it takes 10 hours to get processed in machine 1 and 20 hours to get processed in machine 2. And for Part B, it takes 15 hours to get processed in machine 1 and 15 hours to get processed in machine 2. And for Part C, it takes 20 hours to get processed in machine 1 and 10 hours to get processed in machine 2. Also, each of these parts have corresponding due dates. For example, Part A is due in 24 hours, while Part B and C are due in 48 hours each. And so, as a job scope scheduler, they have two primary objectives here. They want to maximize their throughput while also achieving their customer due dates. Here are the objectives of my senior project. I'm first aiming to minimize the total tardiness of the work orders in the flowshop. Second, I'm also trying to maximize the throughput of a flowshop. Here are the two options we have at hand. The first option is a traditional option, and this is to use a manual planner through subjective scheduling. What this means is to have a person on hand who subjectively decides which jobs to go through the machines at which time. The second option, which is the venue which I will be following, is computer-based scheduling. So here are my deliverables for my senior project. I will be creating a multi-criteria linear programming model which optimizes two KPIs simultaneously. These two KPIs are throughput and total tardiness. I will then be making a comparison to single criterion programs which only optimize one KPI at a time. For example, I will be comparing the output of the multi-criteria model to the single criteria throughput model and to the single criteria total tardiness model. Here is the linear programming formulation of my problem. We have three scenarios here. The first scenario is to maximize the throughput of the flowshop. The second scenario is to minimize the total tardiness of the flowshop. And the third scenario is to minimize tardiness and maximize throughput simultaneously of the flowshop. For all three of these scenarios, they have the same constraints, and the constraints are listed below on the right-hand side. Here is the design and code of my project. To code this project, I used the programming language Python and specifically used the Gurobi optimization suite for the linear programming model. On the top right-hand side, you can see a sample model of my program. You can use the sliders to change the number of jobs and the number of machines in this flowchart. You can also use the slider to change the scenario, and the 3 scenarios as listed before was to maximize throughput, minimize total tardiness, and the multi-criteria model which optimizes for both. Here are the results of my program. So to test my programs, I ran a 20-run test where I compared the results of the 3 different kinds of optimization models. And so for the specifics of this experiment, I ran the program through a 10-job and 10-machine configuration. And so for the results, the multi-criteria model showed a 3.2% improvement of throughput than the single criterion tardiness model. This multi-criteria model also showed a 49.3% improvement in total tardiness than the single criterion throughput model. All 3 of these models ran quite quickly with the maximum runtime of 20 seconds. Also, all the values for total tardiness and throughput for each 3 different models were proven to be statistically different. Here are the conclusions of my project. As seen in the previous slide, the test cases prove that the multiple criteria model provides an effective balance between tardiness and throughput. Manufacturers and business professionals have different priorities when it comes to their KPIs and what metrics they wish to optimize for. Those professionals who wish to optimize for more than one KPI may use my program to come up with a satisfactory solution. Ultimately, this decision support tool can be a great resource to schedulers who traditionally participate in only subjective scheduling. Thank you very much for listening to my presentation. Here is my contact information,